If you look at this classroom, you might remember the exact feeling of staring at a chalkboard, memorizing the rules for sine, cosine, and tangent. We learned the equations, but we almost never learned what physical reality those numbers actually represent. To truly understand them, you just have to think of a simple barcode scanner at a grocery store. When you scan an item, that machine performs a function. It reads the product and outputs a price. Sine, cosine, and tangent are exactly the same thing. They are just mathematical scanners. You input an angle, and the function outputs a hidden physical measurement based on that angle. The dense academic names we force students to memorize completely obscure how simple these physical measurements really are. Before we can take those measurements, we need a stage to measure them on. In trigonometry, that universal reference point is called the unit circle. This diagram shows the exact parameters of that stage. It is a circle with a perfect radius of exactly 1, surrounded by a 360-degree boundary. We use a radius of 1 because multiplying any value by 1 leaves the original value intact, creating a clean baseline. Notice how the degrees map out directions on the grid. We start at 0 degrees, pointing directly horizontal to the right. A quarter turn straight up is 90 degrees, flat to the left is 180, straight down is 270, and a full rotation brings us back to 0 at 360. This pure, flat, two-dimensional circle acts as the universal baseline. Every piece of complex dimensional data we pull from the real world starts right here. So what exactly are those functions scanning for? Let's start with sine. Sine is simply the measurement of a purely vertical line's height inside our circle. Watch this point move along the curve. At 0 degrees, the angle is completely flat, so the vertical height is 0. But as the angle rises toward 90 degrees, the vertical line grows to a maximum height of 1. Cosine executes the inverse, measuring the horizontal line. It starts at 1, but as the angle steepens, this horizontal shadow shrinks to 0. Those intimidating formulas you memorized in school are doing nothing more than tracking the changing lengths of vertical and horizontal shadows inside a circle. But how do we take these flat rules and apply them to the three-dimensional world? Look at the immense scale of this transmission tower. Imagine you need to know exactly how tall it is. You stand 10 feet away from the base, and you look up at the very top. Let's say your line of sight creates a 30-degree angle with the ground. This triangle diagram shows what happens when we feed that 30-degree angle back into our unit circle. The math dictates fixed proportions. The vertical height, our sine, is exactly 0.5, while the horizontal baseline, our cosine, stretches to roughly 0.866. To find the tower's height, we have to bridge the gap between our unit circle and our 10-foot real-world distance. By dividing our 0.5 vertical height by the 0.866 horizontal base, we find a ratio of about 0.57. This tells us that for this specific angle, the vertical side is always 57% as long as the horizontal side. Since we know our actual horizontal distance is 10 feet, we simply apply that 57% ratio to find the vertical measurement. The tower is exactly 5.77 feet tall. We can measure massive physical structures without ever needing a physical measuring tape. All of this assumes our angle stops at a fixed point. But look at this continuously rotating wheel. What happens if the angle never stops at 30 or 90 degrees, but just keeps spinning? This animated graph demonstrates the result. If we record the changing vertical height of our sine function over a continuous period of time, we unspool that circular geometry into an undulating line. This is the birth of the iconic sine wave. Because cosine tracks the horizontal axis, it traces the exact same pattern. It is simply offset out of phase because its value starts at 1 instead of 0. Tangent creates a spiky, irregular waveform because it tracks the hypotenuse, the diagonal line of the triangle. Unlike sine and cosine, which are contained within the circle's radius, this diagonal line must stretch far outside the circle as the angle steepens, eventually reaching toward infinity. By adding the dimension of time, we transform static triangular geometry into the dynamic waveforms that govern modern physics. Look closely at these massive industrial electrical turbines. The physical spinning of these blue rotors relies entirely on those mathematical waves. As the generator spins, it produces alternating current in the exact continuous shape of a sine wave. Even the shifting efficiency of that power grid, the difference between voltage and current, is calculated using a cosine angle. These same mathematical laws also translate down to the microscopic scale, shaping the way we record and process digital data. Consider this vintage tape operator. When we record digital audio, we are physically capturing, manipulating, and storing millions of microscopic sine waves to synthesize complex signals and sound. This oscilloscope display verifies those patterns in real time. If engineers multiply and stack enough specific sine waves at different frequencies, they can synthesize entirely new shapes, constructing the rigid square waves needed for computer processing. The abstract trigonometry drawn onto classroom chalkboards is highly practical. It is the foundational language we use to translate physical geometry into the digital software that runs our world.